My name is David Wimpenny. I'm a Chief Technologist for Component Manufacturing here at the MTC. How many people have been on this site before? Okay, that's good. That means I don't need to explain too much about what's going on. It's a bit, I have to make sure it goes. Okay. So a bit of housekeeping. Please can you switch your mobiles to silent or take the battery out or whatever you have to do to make them quiet. I always struggle with it. I'm sure mine will go off because it does. Facilities. That's a polite way of saying if you need to use the toilets, they are, if you go out of this door here and turn left on yourself or go out of that door, if you left on yourself, you will get to the toilets. At the back, they're equally, you just have to look for the signage. The signage is not too bad in this building, so at least they've given you some idea of where they are. We are not expecting any fire alarms today. So if there is a fire alarm, you'll be exiting by the fire doors here and the fire doors at the top of the stairs. Please look for an MTC host to help you. As I mentioned, AMAZE is the largest and most ambitious metals AM project ever undertaken in Europe. It involved 18 million euros of funding from the FP7 programme, together with industry funding and significant industry input. It's a 4.5-year project which concludes at the end of this month. There's 26 organisations across Europe, research organisations at the forefront of AM technology, and world-leading end users from the aerospace, the space, automotive, and nuclear sectors. There's the logos of the partners in the project. And you can see there's many household names on that list. And you will have today a chance to meet with all of these partners during the coffee breaks and the lunch breaks. And please take the chance to do that. We don't have this assembly of experts very often around Europe. So please take the opportunity to meet with people and network. Anybody here doesn't know what additive manufacturing is? Okay, I'll skip this slide. Otherwise... I don't know. I did a presentation down in London. I got to the end of it, and someone first hand went up and said, "What's additive manufacturing?" And I thought, schoolboy error. So, for those who don't know, we're making parts in layers by depositing a layer upon layer from CAD data. Okay. If you're not too sure, tap the person on your left or right on the shoulder and get them to explain. Hopefully, they'll know. We've got a long way in the last. So I've been involved in additive manufacturing since 1990. We've got a long way in the last 20-odd years. We started with the first stereolithography machine launched in America by Chuck Hull from 3D Systems. And that technology is still in place. It's still being used today. And in fact, this slide's from BAE Systems. We're using this technology to make parts up in Samlesbury, near Preston. We have more materials now. We have thermoplastic materials, we have ceramic materials, and of course we've got metals materials. And actually the focus today is on the metal material technology. Go on, Dimitri. If it's your wife, you can take it. And what's happened is this technology is developed, and it's allowed us then to apply to different applications. So in the early days, additive was used as a way of making prototypes. And because the CAD systems were awful, I mean, they really weren't very good. You couldn't really view things properly. So you'd make a prototype, stick it on a desk, and the design team would review it, and you'd make the changes, even marking the changes on that prototype. We've gone a long way since then. CAD's improved so that the need for prototyping is reducing. Use for casting patterns, still a very important application for additive manufacturing. Printing, either sand molds or ceramic molds. Manufacture of tooling, still a very important application for additive manufacturing. But what we do recognise is the big prize is in direct production, where we're not going to do any of the traditional manufacturing techniques. We're going to go straight in to print the parts that you want to use in the end-use product. And that's the focus of the AMAZE project. Additive allows you unlimited, almost unlimited geometrical freedom. Great production flexibility. There is the principle, not necessarily easy to apply, of print on demand. Very efficient use of materials. So if we compare it to something like machining, we take a big billet of material. We might end up machining away 80% of that material. Whereas with additive manufacturing, the material we use in the product is largely it. We don't tend to waste too much. And finally, material freedom. You'll see some of the flexibility you have in materials, particularly in the academic sessions that are running later on today, where they've tried to exploit the benefits of additive manufacturing to process some really difficult materials, ones which you can't process easily by traditional methods. So, what are the barriers to AM production? Why aren't we actually all using metals AM now to make parts? Well, first of all, we have a limited range of proven materials and associated mechanical property data. We have a poor understanding of the opportunities and requirements for design for AM. Most of us have been taught to design for conventional processes, and they have their limitations, and additive does as well, just a different set of limitations. So we need to educate designers on how to exploit additive to its full. There's limited knowledge of the fundamental principles. I think we like to think we understand additive. But I was in a presentation yesterday. It was the final meeting of the AMAZE project. I learned things from simulations, from in situ measurement of what's happening in the machines, which I couldn't have guessed. So we're learning every day. And we have a lack of industrial case studies. We don't have that history of using additive manufacturing. So the engineer who takes the risk of using that doesn't have anything to fall back on. He doesn't have any case studies to show. The AMAZE project aims to address these and many other barriers to enable the series production of high-performance metallic components. And these are some of the objectives. Large components. And that's not everyone's requirement, but it is a requirement for some end-use sectors. A really important aim is to increase the productivity of metals AM machines, to reduce the scrap and the defect levels in the processes, and reduce the cost of finishing components. At the moment, we can make some very clever, complex parts. I have to say, a lot of them are hand-finished, which to me seems crazy when we've got this wonderful automated process and we have teams of people hand-polishing them to get them to the required quality. And we need to improve the in-process and ex-situ inspection methods, because we know from dealing particularly with the aerospace sector, if you can't inspect the part, you can't use it. You've got to be able to verify, is that part fit for purpose? The scope of activity, it's an end-to-end process, and this is really important. You can't tackle this problem by looking at one part of the process in isolation. You have to look from design for the part, the materials research, improving the AM processes, process modeling, which informs both the design and also the processes themselves in terms of parameters and how the equipment can be improved. Process monitoring control. Many machines are actually running blind. They operate with very little feedback. Now, they are improving, but you wouldn't run a machine tool in the same way that we run some of the additive manufacturing machines. So we have to provide them with more awareness of what's happening in the process. Finishing of parts is a critical part of the process. You can't finish a part, you can't use it. We don't want to have to finish the entire component, machine the entire surface, but we will have to machine certain critical areas like you would do with castings. There's a section on final inspection of the parts, and then finally bring this all together in a demonstration factory where we're using Ganbai Kaizen principles, lean manufacturing principles to streamline the production. We have to deal with additive in the same way we would deal with other manufacturing processes. We can optimize those processes by using very well-established manufacturing principles that we've developed over the last 2 or 3 decades. Has everyone got one of these brochures? If anyone hasn't, hopefully there's still some outside. All of what I've explained is actually detailed in this booklet, so please pick one up. There's links between the AMAZE activity. You'll notice this way the schedule is running today, that we've actually got parallel sessions between the industrial activities and the more research-related activities. They haven't been in isolation during the project, just to make it so we can get it all done in one day. So there's been a really good interplay between the research that's being done and the industrial requirements. And that's really been one of the major benefits that I've seen from this very big project. We've also tried to show how we can use these new processes and materials to actually make components, because that's the acid test. And so in the presentations yesterday, one of the things that came out was how you fixture and finish parts. And it seems to be a Cinderella business. People say, well, I'll take a component, I'll finish it. But actually that can be quite difficult to hold a complex part. And you only understand that when you've gone through the entire process. And then there's the AM factory activity. Again, you'll see some presentations on that. You'll also get a chance to view the facility here on this site that we've developed as part of the project. This is the overview of the day. So we've got these parallel sessions starting. So what will happen is those people who want to do the academic research sessions will leave and go upstairs. There's a room upstairs for those sessions. Those that want to stay and look at the industrial related focused activities will stay here. And you have the opportunity to change between those sessions if you think there's a certain, but try and avoid disturbing things too much. It's quite nerve-wracking for most of the speakers. We don't generally speak to big audiences. So. At lunchtime there'll be the exhibition. There'll be a buffet lunch. There's also, for those that have registered to do tours at lunchtime, we'll be taking you over to the MTC around about 1:30 for a quick half-hour tour of the National AM Centre. Then in the afternoon we've got a session on the demonstration components running alongside the research presentation. And finally at 4 o'clock we're going to have a wrap-up session, and there'll be, for those that weren't able to do the tours at lunchtime, there'll be a final tour of the MTC. We need to make sure that the tours go smoothly. So when we leave at lunchtime, please make sure that those people who are going on the tours get their lunch and also get around the exhibition, because you won't have the opportunity once the tours start. So please make sure you use the time efficiently. We've got lots of exhibition activity next door. We've got a presentation from SI Software.
Sorry, there's a mistake on the slide from me. So you need to be with David at 1:15.
Oh yeah, I haven't got to that point yet. If you get to 1:50, you've missed the tour. So 1:15 in the foyer. Don't worry, I'll be shouting for you. We've got exhibitions from Granta Design, Renishaw, and Theta Tech. and I'll be, say, heading over with the first group of 50 people at 1:15. Okay. Any questions? Running a little bit behind, sorry. You didn't guess that. So one of the disadvantages that I've got being the project technical coordinator. Oh yes, yeah, guys, yeah, please, you're going to go next door. It's time to go now. So. Oh yeah, you can go this way. So if you want to go up the stairs, you can have a shortcut through there. One of my colleagues has pointed out we're actually ahead of schedule. Don't worry, that won't last for long. You know, so we have and we want to give enough time. So one thing we don't want to do is to have a situation where we compress the networking time too much. So without further ado, I'll get on with things. So I get the pleasure of presenting somebody else's slides. So Martin Muir from Airbus was coordinating this piece of work on Design for AM. His planning was quite poor because his wife just had a baby. So he didn't use enough planning ahead, I don't think. We can't really blame him. So I'm going to try my best to present his slides. The good news is the guys that have been involved with this work are in the audience. And if we get any questions, they're going to help me out, I think. So we're going to develop within this particular activity. We're going to develop an automated topological optimization method, investigate free material optimization design algorithms, assess the actual performance of AM structures, because the one thing is modeling them, but do they actually perform that way? And we had some interesting results of work we did actually with ESA on lattice structures, which when we tested them didn't perform in the way we thought they were going to perform in practice. And once we've developed these design tools, we've used those to design the actual demonstration parts you'll see outside and also presented this afternoon. Design for AM is a critical activity. If you're making AM parts that look exactly like the forgings or the castings, you've missed the point. No, the only way to lever the real value additive manufacturing is design for the process. And actually, that's not so easy. As I said, most designers aren't familiar with the things that AM will do and also things that AM won't do. So, we need to find a way of exploiting the geometrical freedom and the material capability that AM offers to produce lighter, high-performance parts which are cheaper to make. And the part performance requirements are actually driving the design. So I think I'd always assume naively that parts are designed to meet a performance specification. And they are to a certain level, but they're not fully optimized. A traditionally designed part will probably have some critical areas where it's designed to meet performance specifications. But because of the cost of optimizing the entire shape for the stress field and the difficulty in manufacturing those parts, often the rest of the part is over-designed. What we can do with Design for AM is we can really optimize the entire part by actually growing it to meet the performance requirements. We do that using topological optimization, lattice or elemental designs. And then we have this automated design tool that actually linked to an FE prediction so that we can actually fully integrate the design process with the performance requirements. And there's, I'm sure I'm going to get shot down here, but I've put, so there's three approaches. Topological optimization, where you take apart, you either reduce it down to meet the requirements, or you actually grow it to meet the requirements. So that's the case here in the top right-hand box. That's an example from one company. We've then got graded lattice-based systems. So that's a lattice example here from Autodesk. These have been moved around. And then we've also got trust-based optimization techniques that we have from limit state here. And these all have their merits. And for certain applications, you want to use trust. For other applications, you might want to use a lattice. And for other applications, you might want to use topological optimization. In some cases, you might want to combine both. So you'll see examples today of parts where you've got topological optimization and also lattice works within the same component. So there's existing design tools. You have to bear in mind that when we started this project, the project was originally written 5.5 years ago. Design tools for design frame were very, very rudimentary at that time. Over the course of the AM project, this project's been running, we've obviously commercial tools have been developed, but they're still not perfect. What you do is you can optimize the design, but then you end up with something you have to re-CAD out. You get something that's really almost a template for the final part. The guys at Alto introduced a shrink wrapping system which goes some way towards solving that problem. But most complex parts, you need to manually redraw them using the sort of rough optimized shape as a template. And also one of the big limitations of current systems, which is partly being addressed now, is manufacturing considerations. When we build components, we need to support certain features. If you end up designing a really complex, clever component, but then it has these supports inside it, you can't remove them. So you need to think about the manufacturing process as you're doing the design. So there's some key technical activities within this program of work within the AMAZE. A study of topological and free material optimization process and algorithms. And then using those tools, optimized components which really exploit the design freedom offered by additive manufacturing to give performance enhancement but also economic savings. One of the great benefits of additive is you can generate really elegant structures which are actually cheaper to make. The less material you have in a part, the cheaper and quicker it is to make. And that's quite different than machining. Let me take this off. It's better. This is some work that's been done by Martin's team down at Airbus in Filton. So I'm sure he would have been able to present it better than me. The end of the work was to develop a set of tools and techniques to speed up the extraction of structurally optimized designs. And that's to do with this fact you get this rough template, but then you have to then generate the real component. And they've taken software tools, commercial software tool sets, and then married those up with customized software which they've developed so you can go from the template to the final object in a seamless process. And those approaches have been used to design some of the demonstration parts that you'll see today with a 90% reduction in the overall design time. So the example would be the Bombardier hinge, where that was designed, most of you have seen it in previous projects where it was designed using the tools that were available there. They've redone that analysis and now they're getting a 90% reduction in that process time for the design process. The guys at Tellers have been doing, had a review of current component design systems based on free material optimization and also XOA software. I have no idea what it is, but I'm sure the guys at Tellers will be able to. I'm going to get a volunteer in a minute. If you have any questions at all, the guys at Tellers are sitting in the second row. Please don't ask me. There's been some really clever work done by Birmingham and Erlangen University to develop a tool set capable of producing true variable density structures through the use of multi-scale optimization and lattice units. And yes, I don't know very much about it. Where the guys from Erlangen and Birmingham, I bet they've gone next door, haven't they? They've escaped. Great. You'll have to try and get them at the lunch break, because there's all different ways of designing products, but it's all driven by achieving a performance requirement. And once we've done this, we need to make sure that what we're predicting in terms of a lattice actually performs correctly. So the guys at Manchester have been taking lattice sections and using X-ray CT to view the processes as they're squeezed to show how the structures actually perform as you compress them, to see if it ties up with the design simulation. And all of these tools have been used to design the demonstration parts, which will be explained in more detail later today. I know you've got lots of questions. I'm hoping that you'll be kind and not ask me too many questions. I'm not particularly au fait with design tools. Can anyone tell me what free material optimization does? Nobody? Okay. Thank you for your attention. My colleague, Jason Dawes, will now talk a little bit about the material characterization and control aspects of the project. How many people here use additive manufacturing machines? Okay, what I can tell you, if you've got powder-based machines and you're not controlling the powder, you will regret it at some stage, probably sooner rather than later. So what's Jason going to talk a little bit about, Dr. Jason Dawes, who heads up our design characterization and testing activity, is how within AMAZE we've developed new characterization tools that are more robust. We've also developed specifications for materials, and how we've applied those in the project to control the materials we've used throughout the project. I knew it'd be you.
I mean, well, you touched earlier in your previous talk about the difficulties with post-processing and getting the surface clean.
Absolutely. So it should be in there as well.
Can you design to take account of difficulties in post-processing as well? Because some of the structures are beautiful, but cleaning them up must be a nightmare.
And they're a nightmare.
So how do you build the post-processing into your design there?
And at the moment, it's not all automated. That's one of the problems. So we need to develop those automated tools. Companies like Autodesk, for many years, have been designing tools to design, design mold tools. And they understand the sort of access issues. And that's what you really want. You want a software system that allows you to predict whether you can access those surfaces. But it's a good question. I don't think all those tools don't exist. At the moment, what people do is look at the part and they say, can I get access to that area and how will I do it? And it's currently a manual process. In this program, we've looked primarily at the build process, not at the finishing process. And interestingly, part of the discussion yesterday on how you fixture a part is if you've got supports left over, or the witness of supports left over from the build process, that can interfere with the fixturing. So it's a really good question, you, but I'm going to try and attempt to answer it properly here. Yeah.
The limit step software, you can consider build orientation in your optimization.
Man, you have to introduce yourself.
But I'll help you out with that.
Go on. So this is
So on the limit steps, that last slide, you can do optimization. That considers your build orientation. So your strategy of minimizing your support. So it does consider your build orientation.
I should have got a manual to do the presentation, clearly. But whatever we do, I mean, this is really critical. The more complex the shape, the more difficulty we have. And so we've got to be very clear about finishing. We cannot finish every surface. It will make the parts too expensive. So we have to think about how we can locally finish the critical surfaces.